Assalamualaikum warahmatullahi wabarakatuh. My name is Niazi Azimi bin Ahmad Maiza and my matrix number is DE220163 and this is video demonstration for section 1 group 2 of class Signals and System BEJ20203. Okay, for this final project, we as a group are going to demonstrate the final project given by our lecturer. So as you can see in your screen right now, this is the task that the lecturer has given to us. So in this video, I will demonstrate on the task number 2 here on the Fourier series analysis of the signals. So we need to plot the signals in time domain for 5, 10, and 20 harmonics. And then we're going to analyze the signal both in time domain and frequency domain. The period of the signal will be given by our lecturer, which is for our group is F0 is 120 kHz. The duty cycle of the signal is set at 50% or tau is equals to 0.5 of T0. So that's all for the briefing on the task number 2. We're going to proceed on the MATLAB coding for the task number 2. But before we proceed onto the MATLAB coding, we will take a look in this manual calculation regarding on the task 2 on Fourier series analysis. So notice that this CO is a complex Fourier series coefficient, which is 0.5, and this Cn is 1 minus e to the power of negative j times n times omega naught times t over 2 divided by j times n times omega naught times t. So all of this equation here, or all of this information we got in CO and Cn, we will put into the MATLAB coding that will be explained later. Alright, so as you can see in your screen right now, we have group members name here, as you can see. Then I'm going to explain first what is this, and in line 11 until line 15. So F0 is frequency given by the lecturer, which is 120 kHz for our group, and capital T is periodic time, omega naught is angular velocity, Cn is Fourier coefficient, and n is integer sequence. So the F0 is 120 times 1000 is same as 120 kHz. So we're going to put in this way. So the T is 1 divided by F0. Pi is set at 3.142. The angular velocity omega naught is 2 pi over t. So this line 22 until line 25 is the function the MATLAB will going to execute, which is we input t is equals to align space 0, t, and 500. Notice that 500 here is our duty cycle. So 50% is equal to 500. So x is equals to t less or same as t divided by 2. So we initialize t1 equals to align space negative 2t, 3t, 5 length, t in the bracket, and semicolon. So we initialize also the function for xt, which is the bracket x, and close the bracket, semicolon also. So for the frequency domain, as you can see in your screen right now, this is this coding, as well as the exponential Fourier series. So notice that the Cn value is the same as the manual calculation that I just showed you just now. So we're going to input the value of the Cn into here, and then we're going to plot into the graph. And this the purple color is the title on the graph, nothing much. For the time domain, we first initialize the k equals to 0, and for t1 equals to align space -2 times t, 3 times t, and 5 times length in the bracket of t. Next, we're going to insert k equals to k plus 1 for the sequence to continue. And then this xn in bracket k, we're going to sum this cn value with this exponent of j times n times omega naught times t1. Next, we're going to plot the graph. So at the bottom here is nothing much, just the graph information. So we're going to hit run. And then notice that at your screen right now, you have 3 figures. So for the harmonics, n equals to 5, this is the frequency domain, and this is the time domain. For the harmonics 10, this is the frequency domain, and this is the time domain. Same also with the harmonics 20, this is the frequency domain, and this is the time domains. So for the analysis, notice that when the harmonics increases in value, the frequency domains also increases, as you can see in this screen. Same also for the time domain. The duty cycle is same, but the graph slope here is significantly increases as the harmonics value increases. So that's all for the analysis part. On the task 2, I will pass the presentation for the next presenter on task 3. So thank you very much.
Hello, my name is Muhammad Akif bin Muhammad Syed. My matrix number is DE220140. Next, I'm going to continue the discussion by explaining about the third question. As you can see from the instruction, you are assigned to construct a low-pass filter using MATLAB with frequency response characteristics as that given in the figure. So based on the instruction, we came up with this code. I will briefly explain each line of the code. First of all, we assign 2 variables, which is FC, which stands for cutoff frequency as 800 kHz. This is happening because based on the instruction given, since we are from group 2 of section 1, we were assigned to FC value of 800 kHz. So that's why we put 800 kHz into FC variable. Now the next variable is G equal to 20, which represent the gain is equal to 20 dB, which also can be referred from this value from the instruction. After assigning those 2 variables, we set the range of the frequency. In this case, we set the range from 0 to 3 kHz by using the log space function and assign those range into f variable. And then by referring to the system, we came up with this transfer function, and we assign the transfer function into h variable. After that, we calculate the gain in dB. As you can see, G multiplied with log 10 absolute h. H is where we assign our transfer function, and we assign the result into gain variable. After calculate the gain, we can plot the frequency response by using the semi-log function. F is where we set the frequency range, gain as we have calculated before, and then we assign the title, the label for x-axis and the label for y-axis, and we write grid on to turn on the grid. So let's run the code. So as you can see, this is the frequency response of the low pass filter with cutoff frequency of 800 kHz. So that's all for the third question.
Assalamualaikum. Now I will explain about task 4, which is analyze the output of the filter box in time domain and frequency domain. Firstly, from the first thing, we need to make a manual calculation, which is firstly we need to identify our FO and FC. FO and FC have been given, which is FO 120 kHz and FC 800 kHz. Next, we need to find the time TO, which is equals to 1 over FO, which is equal 1 over 120, which will get 8.33 kHz. After that, we need to find the torque, I think, equals to TO over 2, which is equals to 1 over 2 FO. After that, equals to 4.17 microsecond. Next, we need to find the T range, which will try to get from xt, then substitute T with 3 different values, which is -1, 0, and 1, which will get this value. Then after that, we need to use our formula, which is xt equals to 1 over TO, integrate with omega plus torque xt e integer watt dt equals to 1 over TO integer torque 0 xt e integer watt dt. Then after we do everything, the last answer will be equals to 1 over TO in bracket 1 over inward bracket -1 plus exponent negative integer watt in bracket torque over 2 close bracket negative e negative exponent negative inward or open bracket 3 torque over 2 plus exponent inward close bracket close bracket.
Hello everyone, my name is Koo Yongjian and I will talk about the task 5 in this final project. In task 5, we have to construct a circuit representing a low pass filter and comparing the output of the filter with the simulation. In a low pass filter RC circuit, it consists of a resistor and a capacitor, and we have to calculate these two values by using the F0 and the FC given in attachment 1. For our group, the F0 given is 120 kHz, while the FC is equal to 800 kHz. By using the formula F0 equal to 1 over 2 pi r square root of 2c and FC equal to 1 over 2 pi rc, we can calculate the value of r and c by using a simultaneous equation. Then only we can use these two values to construct a low pass filter in our circuit. And this is a simulation by using the Proteus software. The input signal is connected to the resistor, and then the output is in between the capacitor and the ground. And after we construct the circuit, then we can set the log graph and to observe the low pass filter that frequency changes by decades. For the graph, it shows that at -3 decibel, the cutoff frequency is equal to 800 kHz, and here 800 kHz, which means that the low pass filter was simulated properly and the input signal will undergo the low pass filter, which caused the frequency above the cutoff frequency, -3 decibel here, will be filtered and becoming smooth and preventing high frequency noise. And that's all from my part. Thank you.
Assalamualaikum. Now I will explain about task 6. Task 6 is about investigate the effect of having a lower or higher duty cycle and set the duty cycle case for case 10%, 20%, 30%, 70%, and 80%. Okay, from here we use the code from task 1, which is this one, and all we need to do is change the duty cycle, which is this T linspace 0T and 500. This 500 we need to change to 500 is equals to 50%, so we need to change to 10%, which is 100, and run this. Save. And we will get this 3 figure. This is for n equals to 20, 10%, n equals to 10 for 10%, and n equals to 5 for 10%. And after that, we need to clear the workspace before doing the other 20%. Then run. We get this 20, 10, and 5. After that, we will record everything, which I already recorded here. This is for 10% and 5 and 10 and 20, 20% and 5 and 10 and 20, 30% and 5 and 10 and 20, 70% and 5 and 10 and 20, and lastly 80% and 5 and 10 and 20. Thank you.
Assalamu alaikum. This is Ammar Amin, and now I'm going to explain about task 7, the circuit construction of an RC filter. We have here to study the different output, the output response at different duty cycles. As you can see here, we have an R and C, and we have an input voltage, controlled voltage source. This is controlled by the pulse generator, and we have a scope to measure the output. We have voltage measurements to go into the scope, and we also have electrical reference and the required blocks by Simscape and electrical libraries in Simulink, the solver configuration and the Power GUI. And now we're going to study the different responses by varying the duty cycle. In this pulse generator, we have a period. This period is 1 by F. F here we put as F resonant frequency, 800,000. And the pulse width will be corresponding to the duty cycle. For example, 10 pulse width is the corresponding to the 10 duty cycle for a period of 1. For one period. Let's see what happens. So this is what happens at we see like a sharp filtering. This is called sharp filtering of the signal at 30%. With a better but still sharp filtering for the signal. At 70%, which is above 50%, 50% is the normal signal, which is half on and half high and half the signal low. This is 70% high. See, we have a better curve here. This is a smoother, so increasing the duty cycle above the 50% will result in a smoother filtering, while decreasing the frequency below 50% will result in a sharp filtering. So this is at 80%. We can see here the maximum for the V out. Maximum V out is 9.9, approximately 1 volt, and the minimum of 0.18. So it goes between 1 and around 2, around 0.2 volts. And we have here other measurements of the signal. We have the frequency, period, and also we have the different duty cycle and so on. Here we can notice that we have a blue and an orange. This is Vn from the voltage control source, and this is the pulse generator. There is slight change when the pulse generates a signal. The voltage controlled doesn't change instantly, but takes time to change. For this problem, I don't know the reason. I've tried using different blocks. For example, the square block. The square block results in perfect pulses, perfect signal, but the problem is we can't change the duty cycle in a square block. So that's why I'm using pulse generator. So this is for the this is in time domain. For the frequency domain analysis, we can use the linearizer model, and we can use Bode plot to plot the frequencies. By the way, I've already set the input for the linearizer model and the output, and now giving the input and output, we get the frequency response. We get the signals at different in the logarithmic plot from 10 to the power of 4 to 10 to the power of 8 hertz. So around 800 here, the resonant frequency, and then we get above for the cutoff frequency. That's all.